So the geocentric, or the Earth-centered theory, was widely accepted as the correct model of the universe for centuries. An astronomer by the name of Ptolemy was responsible for a geocentric model that worked very well for predicting celestial events, such as retrograde motion or the apparent backward motion of planets, as well as the position of planets. For instance, where do I look tonight to see Jupiter? Ptolemy's model uses a series of orbits on orbits called epicycles. So here's an example using Mars. So this is the geocentric model, which puts Earth at the center. And so let's draw a basic circle around the Earth. So this is the basic orbit of Mars, but it gets a little more complex. So Mars is going to be orbiting in this direction, but it's going to look something like this. Let's make Mars red. Here's Mars, and it is actually moving, according to this theory, in a second circular pattern. So not only is it moving around the Earth, but it's moving in a circle as it does it. And so the result, the orbit looks something like this. So it comes around and it makes a loop, comes around and makes a loop, comes around and makes a loop, and so on. Now, something about this picture should bother you. It's really not natural for something to go in circles. Mars would have to be orbiting something. If it was orbiting the Earth alone, it would be going in a mostly circular orbit. We would not see these epicycles, these loops where it apparently goes backwards. Ptolemy varied the size of the epicycles and the speed of the planet around the epicycle so that his system was very accurate in predicting celestial events. Ptolemy's system was widely accepted from about 150 AD until 1543, when a Polish astronomer by the name of Nicolaus Copernicus proposed a sun-centered model of the universe, a heliocentric. Copernicus's model didn't just switch the sun to the center, which we might do this or we might not this year. He offered a very accurate list of the periods of all of the naked eye planets, and a very accurate list of the radii of the planet's orbits. We're going to look at this in depth in the first problem set. The debate between Helio and Geo continued. A Danish astronomer by the name of Tycho Brahe even offered a compromise system where the planets orbited the Earth but the Earth orbited the Sun. His theory was not taken very seriously, but he did make a significant contribution to astronomy by making all of the celestial charts more accurate. How? First, the King of Denmark built him an observatory where he could use much larger instruments, which were permanently mounted in a stable position. Number two, Tycho took into account the refraction, or bending of light as it enters the Earth's atmosphere from space. So to get an idea of what this means, let's draw the curve of the Earth. And we'll say that this dot right here is Tycho, this is his observatory. And then we have the atmosphere. And so the atmosphere causes light to bend. So if you are looking at a star that is directly overhead, you're looking like this, and there's really no bending of the light. But if there is a star over here, here's what's happening. The star is actually something like this, and the atmosphere is causing the light to bend here. And so it looks like this star is here, when in reality the atmosphere bent the light and it's over here. Tycho's not very well known, but Copernicus is easily a Hall of Famer, followed by two more giants of astronomy, Johannes Kepler and Galileo Galilei. Kepler was actually an assistant to Tycho at his observatory and was given the task of accurately plotting the orbit of Mars. Kepler was convinced that the heliocentric model was correct, but he couldn't get his Mars orbit to be as accurate as Tycho's data would predict. He rejected the use of epicycles. Why? Probably because it's circles, extra circles. Eventually, he scrapped all of the old ideas and started from scratch. As a result of his study of the orbit of Mars, Kepler revolutionized the study of planetary motion. His contributions are summarized in Kepler's 3 laws of planetary motion. First law, the law of elliptical orbits, which says the planets orbit the sun in elliptical orbits with the sun at one focus. Kepler actually only knew the orbit of Mars was elliptical, but he extrapolated that finding to include the orbits for other planets. Mathematically, an ellipse is defined as the set of all points in a plane, the sum of whose distances from two fixed points, called foci, and one is a focus, is a constant. So we're going to look at the mathematical terms of an ellipse. And an ellipse is something of this shape. Good enough. So here is the ellipse, and basically we're going to divide it this way and divide it this way. This line, which is going through the longer portion, is known as the major axis. And this line going through the shorter portion of the ellipse is the minor axis. Some letters. A is half of the major axis. So A would be half of the major axis from here to here is A. B is half of the minor axis. From here to here. And C is the distance from the center to a focus. Let's see, we've got two foci. Let's draw one. Let's make a different color. Here's one, and here's one. Now you can figure out the location of these mathematically, but for now it's just a rough sketch. C is the distance from the center to one focus. So this is the basis for an ellipse. Now we have to look at this property called eccentricity, lowercase e, or this is the flatness of an ellipse. There is a formula here. Eccentricity equals C divided by A. So when the eccentricity equals 0, what you have is a circle. Try to draw the circle. And here is both of the foci. They are at the same point. So a circle could technically be an ellipse if both the foci are at the same point, the middle of the circle. If we have an eccentricity of 0.5, so let's say here are my two foci. And something like this. If it's eccentricity of 0.9, the foci are much further away. And you're looking at something more like this. So we have a page with some planetary data, and you might not have it yet. That's all right, I'll give it to you next time I see you. Check the planetary data to find the planet with the largest eccentricity. So I am looking at this paper, and we'll do this together in class. Okay, so on the back side at the very top, the eccentricity of the orbit. If you look through all of these, we find that it's Pluto. Pluto has an eccentricity of 0.249, so it is more elliptical than any other planet. From January 1979 until March of 1999, the farthest planet from the Sun was actually Neptune, because Pluto was in the position of minimum distance of its orbit, the closest point that it would be to the Sun. So let's check the maximum and the minimum orbital radii for Neptune and Pluto. So this is on the front side, and it says distance from the Sun in millions of kilometers. So for Neptune, the maximum distance from the Sun is 5, 7. This is times 10 to the 6 kilometers. Its minimum, 4, 5, 6. Tell you what. Everything on this list is times 10 to the 6 kilometers. So let's put this in parentheses and just use the number from the table. Pluto has a maximum distance 7,375 times 10 to the 6 kilometers. Its minimum distance 4,425 times 10 to the 6 kilometers. So Pluto's closest point to the Sun is closer than Neptune's closest point to the Sun. Of the naked eye planets with sufficient data available, Venus, Mars, Jupiter, Saturn, which one has the largest eccentricity? Again, I'm looking at the back side of this solar system data. Venus 0.007, Mars 0.093, Jupiter 0.049, Saturn 0.056. Which one has the largest eccentricity? And that is Mars. If Kepler had been assigned to study the orbit of Venus, which has an eccentricity of 0.007, instead of Mars at 0.093, he might have concluded that planetary orbits were indeed circles and never have studied astronomy as he did. The closest approach of a planet to the Sun is called its perihelion distance. Perihelion distance. And the greatest distance of the planet from the sun is called the aphelion distance. Aphelion. When a satellite orbits the Earth, its closest position is called the perigee, and its farthest position is the apogee. So some practice. For an ellipse, A equals 12 centimeters and the eccentricity is 0.6. Find the perihelion and aphelion distances. So first off, draw a picture. Always draw a picture. So here is the ellipse. Remember, the sun is at one focus, and the other focus is here. Here's the major axis, and here is the minor axis. So in order to figure out what all we're looking at here, look at this formula. Eccentricity equals C over A. We know the eccentricity. We know A. A is half of the major axis. So this is 12. So eccentricity is 0.6. Here's C. Here's 12. And C equals 7.2. There it is, 7.2. So we're looking for two things. We want to know the perihelion distance. We want to know the aphelion distance. So the perihelion distance would be from here to here, which is really to say the same from here to here. And the aphelion would be from the sun all the way to the other side. Let's draw a second diagram, and this will be very helpful not only for this example, but also for the homework questions. So here's our ellipse, minor axis, major axis. Focus, focus. Half of the major axis is A. Half the major axis is A. Center to one foci is C. Center to, try this again. There's C. And so when you're looking at it like this is helpful. The perihelion. So you don't need to draw this part. But so let's say this is the sun. The perihelion is the closest point to the sun, and that would be here. This is the perihelion distance. And there is a formula for it. If you're looking for this distance, the perihelion is the A, this whole section, minus the C. And that leaves us with the perihelion distance. For the aphelion, here's what we're looking at. If this was the sun, this is the aphelion. And we are looking at this entire distance. So you're looking at a distance of C plus half the major axis, which is A. A plus C. Just as a note, this helps on numbers 5 through 8. So you might refer back to this page when you're working on the problems.